thank you very much for having me at this conference. It's a pity that I can't be there, but with a time difference of 9 hours, that's really impossible. You are doing your thinking while it's night here. So I'd like to talk a bit about contacts between logic and philosophy as a case for scientific methods in philosophy, or even encounters between science and philosophy. And so I hope to take you along a number of examples, show some parallels, maybe sometimes even sort of joint endeavors. And well, that's basically my goal, because, and before I go there, I should also say that my first trip to a real foreign country was actually to Yugoslavia when I was 16-year-old with my best friend from high school. So I still have very warm memories actually from Dubrovnik, because as 16-year-olds, that was the first times we were really far away from home and we were struck by everything. Now, my problem is that I don't have strong a priori views on how philosophy and the sciences should relate. Or maybe I do, but I find them less interesting than something else. If you actually look at the history of contacts between philosophy and scientific fields, that's often much richer and more surprising than what I at least could think of a priori. And the thread I want to follow today of such a contact is in the area of logic, information, and computation. The notion of information is of, or should be of great interest to philosophers. First, it has a long philosophical history. So if you look at the Handbook of the Philosophy of Information, which we edited in 2009, you'll see a chapter where it's actually traced back all the way to Cicero and then through the Middle Ages to modern times. And philosophy had a large role to play in the development of the notion of information as we have it today. But I say the notion, but in fact, as you can see in this handbook, there are different legitimate notions of information in the humanities, the sciences, and even in logic. And it's, to me at least, an interesting and deep conceptual, or if you wish, philosophical problem, whether all these notions amount to the same thing in the right perspective, or whether we should go Carnap's way, who distinguished between probability 1 and probability 2, and eventually admit that we're talking about different notions that may be related, but that we shouldn't try to unify. Before I go there, actually, to me, one of the most interesting contacts between mathematics, logic, and philosophy is the area of intuitionistic logic. I'm not going to talk about that today, although some themes are somewhat intuitionistic, but actually on this view that it's the history and the case studies that are interesting, I actually think that it's always very interesting to analyze how the contact between philosophy and mathematics has gone in the area of intuitionistic logic. Intuitionistic logic definitely started in the foundations of, and even the practice of mathematics, of constructive mathematics. It involved a lot of notions that have become important since. And it seems to me, maybe there are such books, but a sort of assessment what a century of contacts between philosophy and mathematics has brought along the axis of intuitionism would be a very interesting thing to do. However, as I say, I will move on. Let me start with one notion of information, which is very simple, which you can find in logic. A standard example, the restaurant. There's an order which is brought of 3 glasses. So 3 people are sitting at a table. They order 3 glasses, 3 different drinks. Let's say beer, wine, and water. The waiter who takes the order is not the waiter who comes back carrying the 3 glasses. So a new waiter brings them. What do we see? And we see that every time. Like I had dinner with a friend yesterday, you see exactly this. This new waiter has to solve an informational problem. Who gets which glass? And usually that's done by 2 questions. Say, who has the wine? That gets answered. The waiter puts the wine. Then, who has the water? That gets answered. The waiter puts the water. And then you see a little flash of thought in the waiter. And then the 3rd glass is put without a further question. if you wish, on the basis of an inference. So in such simple examples, lots of big issues are hidden. One is how we want to model the information in this scenario. And what seems obvious here is that you could model it as a range of options. Initially, there are 6 ways of putting the 3 glasses for 3 people. And what the answers to the questions do is they update this. So new information is given. Say, once you know where the wine is going to go, the uncertainty of 6 options reduces to 2. It's just, is it water, beer for the other 2 people, or beer, water? And once the second question is answered, the uncertainty has reduced to 1. Okay, so that's why the waiter can in fact put the 3rd glass without asking a further question. So we see the importance of questions in information seeking. And finally, we see a problem which Jaco Hintika called the scandal of deduction. The final valid inference actually doesn't update in the earlier sense. In fact, on the basis of the first 2 answers, the waiter knows who gets the 1st glass, or at least can know it if he pays attention to what has actually been received. But on the other hand, it's a typically valid inference that the 3rd glass has to be for that 3rd remaining person. So what is deduction doing? So what Hintika called the scandal of deduction was that valid inferences, by definition, don't add information, at least not in the semantic sense. That also is a question that we'll return. Now, the theory of semantic information has been developed in various areas, but particularly in epistemic logic. I would think of this as the common sense view of information, at least semantically. And in epistemic logic, you then say that there's knowledge of phi at a particular world or state S. If phi is true in all the worlds in the range of S, where this range refers to some agent who's doing the knowing. So what the waiter knows initially is what's true in all 6 worlds. What he knows after the first answer is what's true in the remaining 2 worlds, and so on. Epistemic logic, I won't go into depth about this, but is an interesting case, at least for me, of the contacts, often spontaneous, between philosophy and other fields, especially when you make the scenarios multi-agent. So, of course, most real scenarios of communication, unlike in the case of the waiter, are multi-agent in the sense that what's also important is what you know about others and so on. And what that again leads to is that in some sense, there is this slogan that 1 + 1 = 3. If you have 2 agents, in some sense there are 3 agents, namely the separate agents plus the group consisting of the 2 agents. So notions of group knowledge become important, like common knowledge. And that's a good example for what I find interesting in the history of ideas. The notion of common knowledge in groups was discovered almost independently around 1970. Philosophers will know it from the work of David Lewis on convention. Economists will know it from the work of Robert Aumann, who actually, it was part of what got him the Nobel Prize in economics. And actually, the earliest source we've been able to find is before Lewis, in a paper in the American Journal of Mathematical Sociology, where the notion of common knowledge is explained, its properties are defined. It's actually a wonderful paper by somebody called Friedel. So there are unplanned, spontaneous, but in some sense significant discoveries of the same notion in philosophy and scientific fields. I find those parallels interesting and worth thinking about. Of course, they have also led to a lot of contacts between these areas later on. But philosophical epistemology, now let's think a bit more about the parallel developments in these various fields. Epistemic logic went its own way. In philosophical epistemology, philosophers came up with ever new notions of knowledge that go beyond the semantic information that I've talked about. Famous, for instance, is Dretski's view that knowledge doesn't refer to the whole range of options that you see. The only thing you need to do is rule out what Dretski calls the relevant alternatives. So you don't have to, if you know that phi, you don't have to rule out all the not phi worlds, but only the relevant ones. Nozick, knowledge as truth tracking belief. So knowledge is a belief that remains counterfactually stable, even if the world were to change. So you're, okay. And then there's lots of versions of knowledge as stable belief under new information, whether that's done qualitatively or quantitatively. This philosophical literature is very rich, and it's only recently that more of it has started penetrating into the epistemic logic area, so contacts can take 1, 2, 3 decades. One interesting thing about all these philosophical analyses I find is that they have an aspect of dynamic action. So Dretske wants you to do something, namely rule out various possibilities before you can make a knowledge claim. And well, maybe with Nozick you could see yourself as an epistemic thermometer that's just attuned. But I think there's actually a sort of dynamic effort involved in staying attuned to the facts. And clearly, if knowledge is something like stable belief under new information or in debates or things like that, again, it's dynamic. This, again, seems to me is a very interesting parallel in a development in philosophy with an emphasis on epistemic action and something that we all know from the sciences. Because it's already a 19th century idea that important scientific notions actually have to be explained in terms of action. So think of the work of Helmholtz, the picture to the left. Helmholtz explained the basic geometrical notions that we have as invariants of the motions that the human body can perform. So the notion itself is static. I could say this object is in between the other two objects, but it arises in a sort of interplay with a dynamic phenomenon, namely motion. And of course, in mathematics, the second picture is Felix Klein. I would say not coincidentally, the same idea comes up in the idea that mathematical theory should always be set up in a double way. That's the famous Erlanger program. So you give the structures, but you also give the transformations. Well, maybe I'm preaching to the converted, but of course also the interplay of dynamics and statics created modern physics. So you see parallels in ideas between philosophy and the sciences. And whenever you realize that, there's interesting things to be done. So I've spent a lot of work, I'm not going to go into that in any detail, in something the area of logical dynamics, where you actually try to study this interplay of action and invariance in logical terms. So I'll give you a few seconds to read this slide, and then I'll move on. But semantic information, it's only my first case of parallels, because there are many other notions of information, even in logic. So let's now talk about correlational information. So for that, a good source is a theory that was proposed as a sort of revolution in semantics, maybe also philosophy, in the early 1980s, situation semantics and situation theory. So here you see an early book, Situations and Attitudes by Barwise and Perry. And to the right, you see a mature book from 1995 by Barwise and Seligman. In situation semantics, the idea is that the universe is a set of situations, which is sort of partial parts of the world. And how can there be information in that universe? Because the universe is full of constraints between situations. So how one situation behaves can actually be correlated with how another situation behaves. Say, all sorts of obvious examples for this. Say, one of the examples would be that I'm watching my video image right now. So I see the room with this audience, but basically the situation that I'm in is me in this office with my computer. But somehow through, well, in fact, a chain of constraints in the world, I'm actually connected to what's happening in your room, and information flows from your room to mine. So the constraints lead to information flow. That's another view of information, I would say, namely correlational information. So by observing one thing, a particular situation or a variable, you actually get information about another thing that may be even physically impossible to reach. As a small aside to the historians among you, what I find very interesting is that a key example in the later work of Barwise is actually millennia old. Well, they had it in terms of hiking in America and a flashlight, but basically it's just this example, mountaintop. I'm at the foot of the mountain and I see smoke at the top. That's an observation I make here, so that smoke is on my... But what the smoke actually tells me is that there is a fire at the top. So by observing something here, I actually get information about what's happening there. So the interesting thing is that this example you can already find in ancient Indian logic 2 millennia ago. So it's also cross-cultural, if you wish. Okay, so what are we to make of this? In the original situation theory, it was very ontological. So the universe really consists of these situations, and the constraints therefore are also real. So we live in a world where there's hidden pieces of rope that tie the situations together. But we could also think of it epistemically. Originally in the situation theory, that wasn't done. It was very anti-epistemic in a way. But in reality, these are just two views of how you could think of situations and how you could think of information channels. For instance, in the restaurant, there's also informational dependencies. The locations of the glasses, if you think of those as separate situations, there's the beer glass situation, the wine glass situation, and so on, they constrain each other. And for instance, sometimes they even functionally constrain each other. The two locations of the wine glass and the water glass determine even the position of the beer glass. So there can even be functional correlations. Okay. Well, I'm very happy that at the end of that trajectory, actually these views did come together, like in a paper I wrote with John Barwise in 1999 in the JSL, where actually we use techniques from modal logic, so which definitely comes more from the originally, in my work at least, from the epistemic realm, were used to discuss, if you wish, situation theoretic themes. There's other situation theory themes which we might go to in discussion, because situation theory, I think, it had lots of great ideas that again have taken decades to develop in their mature form. One of them is circularity and non-well-foundedness, and at least I, maybe a bit idiosyncratically, but see a straight line from situation theoretic work on non-well-foundedness to Coalgebra. But this is an aside. Now, correlation is also at the heart of a modern view of, or a modern theme in logic, namely the area of dependence logics. And so this was pioneered by Jouko Väinänen in his 2007 book. And recently, I've also started publishing on this with Alexander Baltag on logics of dependence. So maybe just to give you a flavor, because the question is, if you're a logician, you try to think of the simplest way in which you actually could model a phenomenon like correlation. So here's one way of thinking about that. Let's define a team as a set of assignments of values to variables. So now our situations or locations are just the variables. So these variables go to values in their range. These functions do that for all variables, but we don't put all the functions from variables to objects. There are gaps. So what that means is that you cannot always independently in your universe of assignments vary the value for one variable while leaving all the others the same. Because if there are gaps, it might be that that function is not, that assignment is not available. The only assignment that may be available is one which changes, let's say, the value of x for you, but you also got to change the value of y to get to another available assignment. Then you have correlation. That's exactly, in some simplest sense, what correlation is. It's gaps in the total behavior that could happen a priori. Functional dependence is the special case that if you have the local values fixed, so you're in a state of the system or an assignment, and you keep the values of the variables in the set X fixed, so you only look at states T that give the same values to the variables X, that in that case, you also have that S agrees on Y. What that means is, if you know the values of the X's, you automatically know the values of the Y's. That's the epistemic interpretation of dependence. Or if you want to think ontologically, then it's just that in your world, where these states really exist, the only way of actually shifting over, maybe even physically, from situation S to a situation T, which still agrees on the X values. Maybe these are keys on your computer that you've pressed, but you change the rest, and you will see that when you press the X keys on your keyboard, automatically the Y key also stays the same. Now, logicians introduce syntax, so here's a bit of syntax. It's actually more or less the syntax of first order logic. You can then interpret this language. I'm not going to go into details. And basically, this is of course what logicians do. You get a small logic of functional dependence, which is axiomatizable and decidable. Why? So this is an example of a technical logical perspective. Is that any good for the larger conceptual questions about correlation? Well, here's something that I at least would find significant as a logician. Of course, if you want to talk about dependence, you probably also want to talk about independence. What's independence? Physically, it is that X can do its own thing and Y can do its own thing, and there's no physical constraint in how the two things behave. Epistemically, what it means is that if you know the values of X, you still don't know anything about the value of Y. The value of, so even if you know what the X's are, maybe they have the values 1, 2, 3, then Y is still free in the system to take on any value it wants. Okay. Now, this we can also formalize. We can extend the logic, and now suddenly we find that the combined logic of dependence and independence is undecidable. What that means is that there are computational subtleties. Dependence isn't such a complicated notion. Dependence and independence is. I think that somehow gives the feeling that thanks to the logical analysis, we dig a bit more deeply into the conceptual nature of dependence and independence. Let's generalize a bit from here, and maybe I should also quickly summarize. So far I've talked about semantic information as a case where it's, if you wish, a sort of common sense notion. You can formalize it in epistemic logic, and it's an interesting case for me where philosophy and other disciplines meet and can exchange ideas, like in the dynamics. Dependence is another such area. It's pervasive. It's everywhere, dependence. The first significant putting on the agenda of dependence I see as happening in philosophy, in Bauer's and Perry's book, Situations and Attitudes, but I've shown you a little bit of how you can go further and further also by bringing some logical tools to bear. Now, let's step up the scientific tools we want to use in studies like this, and let's talk a bit about epistemic topology, a sort of current movement. In the dependence logics, as I've described it to you, there is a sort of assumption that the values which these variables can take are sharp. So, say if the variable is location of wine glass, then there's only 3 values which it can have, in front of one of the 3 persons in the restaurant. Sharp. Well, if we also take empirical inquiry seriously, then sharp values are normally speaking not attainable. The best we can do is measure nature, and measurement yields ranges, right? So if I measure something, I'll see a little interval. And what's crucial then, if you want to think about epistemic notions in that setting, is approximation. So I may never know the true value of a variable, but through measurement, by the way, again, a dynamic action, also in this area, the dynamics is essential. Through measurement, I can zoom in closer and closer on the actual value. But in general, this could be an infinite process. So we also have to think about limit processes in inquiry. All these are things that have been studied or are being studied in formal epistemology. And yeah, I just want to enlarge on this example a little bit. So empirical inquiry then has some features which are not like my restaurant example. It's about measurement, approximation, limit processes. That's crucial in the sciences, but also, for instance, in margin of error views of knowledge, like Tim Williamson, whom I put here. Now, how to model this? Here again, science comes to the rescue because it can be modeled in topology, as has long been known. To the right, you see two founding fathers of topology. So the possible outcomes of measurements or observations can be modeled as open sets in a topology. And if you make the open set smaller, then you're actually in a process of approximation. Now, the connections between topology and philosophy, I actually don't know, maybe Hannes knows more, but between topology and logic are definitely very old. There's work by Vickers on logic and topology. There's work in the 1990s by Parikh and Moss on using topology to describe what they call epistemic effort. And of course, when all is said and done, intuitionistic logic has had connections with topology since the 1930s, which was realized by Tarski. So what we now need to look at is our topologies of information states. That's one way of thinking about it. So then it's the topology of the open sets, which are the outcomes of measurements. Or this is another possible interpretation, which also goes back to intuitionistic logic already. You could also think of it as stages in the temporal history of inquiry. This is just an aside, maybe mainly to show you this picture. So I'm not going to expand on the connection with formal learning theory. To the left, you see the book of Kevin Kelly, which is a sort of pioneering book from '96. And to the right, you see a picture of Kevin and me with Jaakko Hintikka at a Helsinki meeting of the large logic and philosophy of science, methodology of science Congress. So notice in particular that Kevin and I are on our knees. I leave it to you to interpret what this means. But approximation is one thing. But if approximation is to be epistemically useful, then we've got to have some sort of guarantee. Let's think, for instance, about a dependence. So y depends on x. That suggests, as I said in the beginning on the epistemic interpretation, that if I know the value of x, I know the value of y. But that was the sharp value thinking. Now I'm in a setting of real inquiry, so those sharp values I'll never have. But what I would want to say is that I can approximate the value of y to any desired degree by approximating, by making the right measurements on x. And you see it coming, of course. Now we're at a basic notion at the heart of topology, namely continuity. So not just any dependence, but a continuous dependence is one which actually allows us to approximate y to any desired degree by approximating x. So now suddenly our epistemology connects to a key notion in topology. It's about continuous functions. But we can go further, because I'm now referring to a paper I'm writing with Alexander. Okay. If the function is continuous and you interpret this now more conceptually or philosophically, what you know is that measurement of x is going to approach the true value of y. But that may still not be epistemically very useful. This just gives you a sort of moral support, like do your approximation and in the limit you will find it, but you don't know how to approximate to get a particular degree of approximation. And again, so you would like to convert that know that into know how. What is the degree of precision for x I need to get in order to arrive at a required degree of precision for y. And again, we're in topology, or maybe analysis, because then we need something stronger than continuity. We need uniform continuity. Uniform continuity for the mathematicians among you lets the epsilons, let the deltas depend on the epsilons, but not on the current point where you are. It just works uniformly across the whole space, or at least locally, maybe across a part of the space. So another parallel. Key notions that were developed in mathematics in the 19th century also correspond to key desiderata one might want to have in an epistemic analysis of inquiry. What about independence? This is just a small aside, and I should also probably not take too long over this. What's independence in the topological setting? Independence is that no matter how well I measure X, I learn nothing about Y. That means that no matter how small I make in, again, terms for the mathematicians, my delta, F could still take on any value in that small range. Functions like this are known in analysis. They're called everywhere surjective. Very interesting part. They are about the opposite of continuous functions. And independence would actually correspond to unlearnable things in the universe. Now, at least I leave that to you, that's my small excursion. In my private philosophy, optimism and pessimism belong together. So continuity and uniform continuity are about epistemic optimism, being able to actually find through values through measurement. Independence and everywhere subjective functions about pessimism, about things we'll never find out. And that's why I corrected David Hilbert a little bit with his famous quote, "Wir müssen wissen, wir werden wissen." I would say what Hilbert forgot was that in other parts of the universe, we shouldn't know and we won't know. We can also do this in logic, but I'm going to skip this. So the result of all this is epistemic topology, sort of interface field. It's much richer than what I said here. And it has two faces, like a real interface. It offers a sort of mixture of conceptual and mathematical analysis of epistemic notions. It's an area where philosophy and science can work together and influence each other both ways. I'm going to look at my time and see, yeah, I think I still have some time for my last example and my conclusion. So far, this was all about semantic notions of information. Let me say a little bit about another notion of computation, of information, which also goes back to what I said about Hintika's scandal of deduction, which might just as well have been called the scandal of computation. So, for instance, what is an inference doing? Suppose that you perform a modus ponens inference. So phi implies psi, you have phi. And now you actually draw the conclusion that psi. That drawing is obviously an action. You're doing something. But on the semantic view, you're doing nothing. Because if you have phi and if phi then psi, and if you've updated with those, nothing is going to change in your semantic range by also stating psi. But of course, that can't be right. Because we do perform inferences, and it's very useful to us. Well, one answer is that the reason is that there's another notion of information at work here, which I would dub information as code. Concrete computation works on code, say linguistic formulations or other forms of code, and so does concrete deduction. That brings us to connections with the theory of computation and what the information means there. And then many of the themes I've talked about in epistemic topology or earlier on need to be rethought. So I've put some pictures here. Of course, everyone knows the iconic one to the left. That's Alan Turing. Does anyone know who the one to the right is?
Gensen.
Sorry?
Gensen.
No, the one in the middle is Gensen, actually, but okay, you could predict Gensen somewhere. And the one to the right is Kolmogorov. Okay, I'll just briefly talk about one issue. What information is provided by computation and deduction? I think this is a sort of major question to which maybe the problem is not that it has no answer, but that it has too many answers. But let me just point at one line which I'm personally interested in. You might think that what an inference does, a valid inference, is that improves your access to the semantic information. It gives you a further description. The range has stayed the same. But what the code or the language does is it gives you more of a grip on what the range looks like. So I call that access. And you could think of inferences as improving your access to the semantic information. Then you can think of the dynamics of proof and inference as a sort of access dynamics. You get better descriptions, which you could also, in terms of rearranging code, do various things with. And it's a sort of dynamics on top of the semantic dynamics. Notice that this is not a conflict, right? So the semantic information is not in conflict with this sort of information. The real question is how they cooperate. But this also fits in with a lot of current work on the dynamics of awareness and attention. So especially in economics, but also in computer science, people have started focusing on the fact that it's all well and good to talk about epistemic scenarios, but we only have a certain amount of attention to spare for what we're thinking about. And what we're thinking about is formulated in certain ways, and those formulations are important. The framing of the situation is extremely important. So then you have to think about how would you model awareness and attention. That's a big topic, there's proposals, but I would think then we're in the midst of current discussions, which again play in different fields at the same time. Logic, philosophy, computer science, economics. I'm not saying, by the way, that you couldn't have a semantic view on computation. This is, again, a bit more of an aside, but I have also been interested recently with Alexandru in analyzing domain theory, which is actually a theory from the 70s, which is more semantic theory of what computation does, but let that be an aside. So what's then the total picture that I'm talking about if you take the information theme at the interface of logic, philosophy, and the sciences? There's a sort of landscape of use of information, which maybe goes back to Carnap, I don't know. From syntax and code, the most fine-grained view of information, to just sets or ranges, what I started with, the least fine-grained. There's many intermediate levels where you could work: plausibility models, probability, algebraic approaches. The landscape has no preferred direction. This you can see in science. So many people think that things get better if you make your analyses more detailed. That will be the direction from less fine-grained to more fine-grained. But actually that's not true, because if you look at the history of science, some major discoveries arose precisely because people did the opposite thing. They abstracted away from fine grain and went to coarser grain. In fact, topology is a very good example, because it's a coarse-grained, in fact, extremely coarse-grained abstraction out of analysis, but of course, immensely illuminating. So both directions, finer grain, coarser grain, lots of things to be discovered by both, I would say, philosophers and mathematicians or scientists. This again is just a throw out to the audience. I said that situation theory had other themes than correlation, for instance, circularity. And I mentioned that I would see the modern interface of that as Coalgebra. I personally believe, I just wanted to go on record on this recorded Zoom meeting, that I think that Coalgebra is another theme in science, in this case computer science, whose repercussions still have to become felt in philosophy more than they have so far. Although I know that there are some people at your conference who already see this and work on this. I believe Coalgebra is going to have a big impact on our views of meaning, but having gone on record as saying that, I move on to the end of my talk. Conclusion. I've just given you a particular case study. I would say that encounters of philosophy and the sciences are ubiquitous, and they're often not as well known as they should be. We follow just one strand. I've talked a bit about some topics at the interface of logic, information, knowledge, and computation. You could also have 7 lectures about in the same style as mine right now, because many more stories of this sort can be told. In fact, in the Handbook of the Philosophy of Logic, I have a chapter on logic in philosophy where I give about 5 such stories for a number of different themes at the interface of logic and philosophy. And I believe, because I thought I was not going to do this, I think I'm going to stop and I'm going to say, I hope that my case studies show how interesting the contact can be between philosophy and the sciences when you look at concrete themes. The history keeps moving. Sometimes maybe the philosophy is more active with new ideas, sometimes the scientific side, but the encounters keep going. Does any general conclusion follow from this about how we should view the contact between scientific methods or science and philosophy? Maybe it does. Maybe I even have views about it, but I don't think that's my topic for today. Thank you very much.
Thank you very much. And so now the question. If there are questions from either from the audience here in Dubrovnik or online, maybe just as one initial question, if I may, maybe to come back to the beginning of your lecture. Could you put a question on priority, say, between invariance and dynamics, be it on epistemic level or ontological level? How do you see this relation? Invariance, yes, it's invariance on one side, and motion or dynamics.
The priority, yes.
Philosophy, for example, closer to invariance, or it is simply indifferent?
Well, so I couldn't give a uniform answer. For instance, in the case of, I'm not totally sure about Helmholtz's own views, but in the case of the geometrical notions as invariance of motion, you might think that the dynamics comes first, so that the humans are just have these bodily, physical possibilities of movement, right? Say, walking in a straight line, turning around, so that already gives you translations and rotations. I'm not quite sure what reflections are, but maybe it's this. And then you could think, well, in a secondary sense, the invariants are picked up. But I think there's also cases where you really want to think of it as just coming together. In fact, in the Erlanger program, I don't think that there's a priority between, let's say, the static structures and the dynamic transformations. Does that address your question? Or so it depends a bit on in which area you're interested in transformations and invariants. For instance, say in the case of epistemology, it's also interesting. Suppose that you think of knowledge as an invariant of information gathering, right? Let's say knowledge is a highly invariant form of belief. Then again, you could think of that historically. Is that really true, that we first have the information gathering and then maybe those notions were recognized and words were put in the language, like to know? Or maybe was it the other way around, that humans are capable of having attitudes? So once you have them, you see them and you start manipulating them. That's also very human. I just don't know. Those are interesting questions.
So here we have in the audience in Google.
I've got a general question about progress in philosophy. Can we say that within the logic or topology or some formal tools, we've got some real contribution to philosophy and real progress in philosophy, or rather not?
Are you now asking me about my view of epistemic topology?
My question is general and is about the progress in philosophy.
Yeah.
the logic within topology and with use of that kind of formal tools, can we say that we have a real, let's say, contribution to philosophy, and we've got some progress in philosophy, or philosophical practice is like a shaving? Yes, you need to do that, but there is no real contribution, you know, besides you are shaved. Yes, and that is a question about philosophical progress.
Yeah, no, I see what you're asking. Yeah, okay, that's one of those big questions that I really have to think about. Okay, so there's definitely, you could say, progress in science. Say, take the case of mathematics and topology. The coming of topology, I'm not exactly sure what progress is, but it was definitely progress. You feel you understand a lot more, and now at the right abstraction level, that's what topology does for you in a lot of areas. Of course, not everywhere, but in a lot of areas of mathematics. If you take my case study, so could epistemology also be capable of progress? I personally would say yes. Actually, I do think that if I compare epistemology in the 1960s, when it was, let's say, Plato's view, knowledge as justified true belief, and okay, old age, I'm blocking on, give me the Gettier counterexamples, okay? And if I look at the area of epistemology nowadays, 5 decades later, I think it's immeasurably richer. So basically, I'm an enormous admirer of the work of Brzezinski, whom I mentioned, of Nozick, of well, many other authors, so Stallmaker and so on, who have all contributed various things to. The only thing is that maybe there's a little problem I sometimes feel with, and it comes to the last slide, which I hid because I thought it might be too controversial. Philosophers themselves sometimes don't see this progress in epistemology because they think that there's one true philosophical analysis of what knowledge is. And then, of course, having 5 interesting theories is not progress, but it's a problem. And those theories should first fight it out. But, of course, the mentality in science, and I think also in logic, is one of not fight, but fit. I actually think that all these different accounts of knowledge are not competing theories. They each bring out aspects of knowledge that hadn't been realized before, at least not in that clarity. So I think that a growing richness of philosophical analyses of aspects of knowledge, just one example, is definite progress. Epistemology in the year 2020, to me, has progressed measurably compared to epistemology in the 1960s.
Maybe you can come closer to so that we can hear clearer.
So I was just curious about your statement concerning how you can combine the fine grain and the coarse grain approach in the case of compositionality. So could you say a bit more about that?
Wait a minute. That's an interesting question, and I'll say straight away, I don't have an answer to that because I hadn't thought of that. I hadn't thought when I put this slide, at least, and I mentioned compositionality. If this is the slide you're referring to, I had another thing in mind, namely. So your other question I'm not answering. I'd have to think about it. A good question, but maybe I can say something about this slide. I think a lot of theories of compositionality actually have a sort of bottom-up construction view in mind. So you start with simplest meanings, and then compositionally you go to more complex meanings given by more complex expressions, or at least maybe the meanings are not more complex, but at least the construction process is more complex. So that's inside out or bottom up. And that fits with an algebraic point of view on compositionality. But in Coalgebra, you think the other way around. You have objects that you may not even be able to analyze down to the bottom because either they're infinite or they're infinitely complex in other ways, but you observe them outside in. And that's actually a very different view of what sentence analysis is because then, this is in a paper I've written with Doug Westerstaal and Alexandru, then basically there is no bottom level to look for. It's more that from the outside, looking from the outside, you see more and more structure. So we have a sort of a tip of the iceberg view there. The sentence that you see is sort of tip of the iceberg of a mental process. We can analyze more, but it's always in a co-algebraic way. There is no endpoint. What that means in the paper, but then I'd have to go into too much detail, is that we actually think that this also resolves the tension which you find in debates between Frege's two principles, compositionality and contextuality. We think on co-algebraic perspective, those things smoothen out. But I refer to that paper, which I can send you if you're interested in details of how this works.